2, 1. Okay, next up is LeChatelier's principle. Now, this part 1 and part 2 are both going to not involve mathematics but logic. And this may just bring chills down to some of your spines. And, generally, I find that people that like math tend to like logic, but not as much as people who don't like math. They prefer this. But you've got to think through 3 areas. One deals with concentration. And what I mean by that is this. LeChatelier decided that something was really weird about how things changed when certain parts of an equilibrium reaction were changed. In other words, he found that if you were to change the temperature, the reaction would shift. He found that if you changed the pressure, the reaction would shift. He found that if you changed one of the concentrations in the reaction would shift away from what it was. And then eventually, in the case of the concentration, eventually it would create a situation where the original value of K stayed, where in the case of the pressure and the temperature, the value of K actually changed because the conditions in which the reaction being run were changed, whereas if you had concentration, the temperature and the pressure was the same, and therefore there were no change in concentrations, and therefore no change in K. That's what this is all about. So LeChatelier, and this is how you spell it, and it's pronounced LeChatelier, those wacky French and their verbiages, is a guide to understanding how it's going to change and how we can predict certain things to occur. Okay? So, in fact, there was another guy by the name of Carl Ferdinand Braun. Well, I don't think Germany was around then, but I think probably Russia also discovered these theory-seeing relationships with LeChatelier. I guess had a better PR person. But we're looking at 6 areas of studies, 3 of which that we're going to spend the most time on: concentration, temperature, and pressure, and volume to a little bit. And then catalysts and inert gases would actually have no effect upon it. If you put an inert gas in a reaction or a catalyst to make it go faster, it doesn't really affect the overall reaction, but it was discussed by LeChatelier. But we're going to concentrate on concentration, temperature, and pressure. Okay? All right, so let's talk about concentration of components within a reaction. Let's take a look at something called the Haber's process. Now, Haber was an extremely famous scientist. And the first thing that he was famous for is for this reaction that we're about to show. A very simple reaction, nothing really complex. And that is that nitrogen gas reacts with hydrogen gas to form ammonia gas. Now, why is this such an important reaction? Well, for those who are involved in the agricultural area, you know that ammonia is a major component of fertilizer. Nitrates and ammonias are both highly sought for components, but particularly ammonia. Why? Well, plants have proteins like humans and animals and such, but their proteins are a little bit different, but all proteins need nitrogen to exist. Amino acid, the amino part of amino acids means nitrogen or NH components within the compound. Acids we'll get into later deals with hydrogens by themselves. This reaction right here, it creates pure ammonia, and nitrogen can come right out of the atmosphere. Hydrogen can come out of many substances that contain hydrogen. You won't find the atmosphere is too light, it goes right out in space. This is the most abundant element in the universes, if you wish to call it that, or universe. 99% of all elements in the universe is hydrogen. The other 1% is helium, and then smatterings of all the others across the universe. So this is really easily found. Both of these are easy. This is found in nitrogen. It's found in the atmosphere, about 77-78% of our atmosphere is made of this stuff. So this should be really easy to do. It's not. And the reason why is because the K value for this is less than 1. Meaning, we're going to get products more than the reactants. We want reactants, we don't want these products. So Haber decided that, hey, maybe I can do something to fix this. Well, what motivated him outside of maybe people starving or the price of fertilizer being too high? The biggest thing was World War I. In World War I, troops were sent to the front to battle the French and the British in the beginning. There was no food for the rest of the residents of Germany because they couldn't make enough. There wasn't enough ammonia, not enough fertilizer. So he decided that this is a major disaster and he's going to fix this problem. So he did this in 3 ways. The 3 ways we talked about. Concentration, which we're talking about right now, pressure and temperature, as you see. So he found that if he could find a way to siphon this stuff off as soon as it's made, that left a hole here. Now, why is that important? Well, you know, Kc is equal to the concentration of NH3 squared over the concentration of N2 times the concentration of H2 cubed. And so you're going, well, okay, well, you said there's no math. Well, there really isn't. Maybe a little thinking in terms of math, but you're not going to be doing any crunching on the calculators. If you decrease this, let's just say this reaction is at equilibrium, you get whatever value it's supposed to be, some number less than 1. And you start siphoning this stuff away, well, that causes this to decrease. That means you no longer have the Kc value you had before. And it doesn't like that. It wants the original Kc. So, that means then that we now have a Kc, I'll call it Kc prime, is less than the original Kc, which I'll just call Kc. And so, inherently, it will not accept that, so what it's going to do is going to churn, these two are going to shift more, going to create more to go to the right to fill the hole, because now we have, that will increase this over here, causing this to decrease here until it reaches the original value of Kc. So, if he can find a way to do this, and there are ways of doing that, you could put it in a vat of water, gigantic vat of water, have it bubble through that, it will bond, and they're not very great, but better than just floating around where you can't get it. You could also do other things with it, which we'll talk about again later. And you can get this constant shift of pushing this stuff forward using this idea. It's a brilliant idea. Okay, so this is what's happening then. When you decrease a component, like this right here, the reaction shifts towards the decrease. The best analogy is if you were to take your little niece or nephew over to the beach and you want to dig, let's say, you want to dig a hole into the ground, into the sand. You want to see if you can get to China. Ooh, that'd be fun if we go to China and talk to little Chinese children. And you dig and you dig and dig. What happens as you get deeper and deeper in there? The sand starts to fill in. The beach is one gigantic equilibrium system. It doesn't like holes in it. So it fills in automatically because it's so, shall we say, soft, not bonding to each other. And because there's no cohesiveness to it, unless it's wet, of course, we're assuming it's a dry beach, it's while you're there, it's going to fill in on its own. That's what equilibrium does. Same thing here. You decrease it, it's going to shift towards that decrease. That's LeChatelier's principle. Now, the opposite is exactly the same thing. Now, it wouldn't work in this reaction, but let's just suppose that you dumped in more NH3. That's going to make this bigger. Making this bigger, doesn't like it, so it's going to shift away to the left. We call this shifting to the right as it goes to the products, shifting to the left when it goes to the reactants. So if a concentration of an equilibrium substance is decreased then, the reaction shifts toward that decrease. And the opposite happens too, about if you were to increase. Now, this time you decide, okay, going to China was really stupid, I'm sorry I put you through that. So let's go make the biggest sand mountain we can ever build. Ooh, that'll be fun. Okay, so you start digging and plopping stuff on top and more. And the more you dump sand on top of the mountain, what happens to that mountain of sand? It scoots away. It shifts away from the increase. Same thing here with equilibrium reactions. If a concentration of an equilibrium substance is increased, like making that mountain of sand, then the reaction shifts towards, now it should be away from that increase. So it's going to shift away from an increase and it's going to shift towards a decrease. Alright, so let's take a look at a situation with problem number 65 on page 687. Okay, so here we have an equilibrium reaction. We have a certain value K, whatever it is, doesn't make any difference. It says the carbon dioxide is removed. Okay, this is just like the Haber process. Remove the stuff, direction of the equilibrium shift is going to be what? It's going to be towards that carbon dioxide. You're building a hole to China in the sand. It's not going to work. And therefore, the shift is to the right. Okay, this last section in this chapter deals with LeChatelier's principle again. Only the second part of this discussion now deals with changes in conditions. That involves temperature and pressure. Now, last time we dealt with changes in concentration, and that did not change the value of Kc. This, however, will change the value of Kc, and we'll talk about that. But the most important part about this is talking about how the reaction is going to change according to the conditional changes, and then we'll talk about how Kc changes. Now, because of that, we're going to be looking at the direction that reaction itself causes because of something beyond what the K value is. So let's talk about temperature first by looking at Haber's process one more time. Now remember, in Haber's process, that N2 gas plus 3H2 gas produces 2NH3 gas. Now, let's say that this reaction is exothermic. So we'll give it a value of somewhere in the neighborhood of -25 kilojoules